Hello.
Yes, sir.
Can we start? Deepnarayan, are you present in the class?
Yes, sir.
Konko,
Yes, sir.
Subro,
Yes, sir.
so Partho, you have got my connection, no?
Yes, sir.
Rohan,
Yes, sir.
Ananya,
Yes, sir.
Konko, you have entered. Your name is given here twice. Why?
Sir, I'm not sure about it.
So PowerPoint is visible.
Yes, sir.
So today we are going to discuss some algorithm of single variable optimization. In the last class, I have discussed the NLP of any engineering design problem where we have already determined the objective function which is to be minimized or maximized. In real life, the problem will be constraint optimization problem where the design should satisfy certain constraints along with the minimization and maximization of the objective function. But for learning process, we have to learn first unconstrained algorithm where there will be no constraint at all. Only we have to find out minima or maxima of a given objective function. Then later we will learn how to tackle constraint along with the minimization and maximization of objective function. So now I am going to discuss unconstrained optimization algorithm, and another aspect of is there the objective function is a single variable objective function. Later we will learn multivariable objective function, but now we are starting with single variable unconstrained optimization problem. Is there any question? Hello?
No, sir.
So suppose we will use some numerical methods while searching the minima or maxima of a given function. There are certain standard procedure in classical mathematics or traditional mathematics from where we can get the minima or maxima. But generally in optimization algorithm in real life problem, we use numerical methods. There are certain advantage of numerical methods over the classical methods. You know, I think already. And what is meant by numerical method? Suppose a function is given for which we have to find out the derivative. The function is x square. We know that it can be evaluated directly. The derivative is 2x. And at the point 2, x is equal to 2, the value of the derivative is 4. But if we like to evaluate the derivative using some numerical method, then we have to use this expression that derivative f1x is given by f of x plus delta x minus fx by delta x, and the delta x value or value of delta x will be very small, like 0.01. And now for calculating derivative, we have to evaluate the function only. Here we have used the value of function only at a point x plus delta x and at another point x. So two function value has been evaluated, and then from the expression derivative can be calculated as shown here, and it is obtained as 4.1. So if we calculate directly from the formula, the derivative is coming to be 4, But if we use numerical method, then we need not to know the expression of the derivative. Only we have to evaluate the function value. But there may be some error, like here error is 0.1. But this error can be minimized, or this error can be reduced to our desired accuracy. It is shown in the letter that if you choose delta x instead of 0.01, if you choose 0.001, then in the derivative value will be 4.001. So error will be from 0.1 to 0.001. 100% it is reduced. Is it understood?
Yes, sir.
So we use numerical method because in some problems the calculation of derivative of the function will be difficult. Directly calculation from the classical method will be difficult, but we can evaluate the function. And as we can evaluate the function, so we can estimate the derivative value from numerical methods. Is it acceptable? Hello?
Yes, sir.
So using numerical method, it will be approximate, but approximation can be controlled. And approximation can be reduced to our desired accuracy level. And in engineering problem, we require solution with certain accuracy. The problem need not require to get a 100% virgin solution where there will be no error at all. Instead of that, with desired accuracy, if any solution is obtained, that will be applied. This is the general approach. So here I have discussed some points. You will go through the comparison between classical techniques and numerical methods. Now, what is the basic philosophy in searching minima or maxima using a numerical method? Suppose the objective function is given. We have to start with an initial solution, initial trial point x1. So within the given interval, search interval, we have to choose an initial point. In the function you look, the optima is given at this point. Suppose at this point, we can start with some initial point. Initial point may be arbitrary, or initial point sometime in some certain algorithm, initial point may be selected with certain logic. And after getting the initial point x1, now we have to find out certain search direction. In this case, if it is a single variable function, search direction is only one, either in the right side or left side or in the along the x-axis. So either positive or negative. So search direction is not confusion here, but in case of multivariable, we will see later that first of all we have to identify the best search direction among several search directions, because in case of multivariable the search direction will be infinite number of search directions are possible. But here in case of single variable, only one search direction is there. But the question is, what will be the next best possible point? What will be the next best possible point? Our target is to get minima of the function. So what will be the next possible point where the function value will be improved? Improved means in case of minima, it will be reduced. So that will be my next trial point, xi plus 1. So xi plus 1 is equal to xi plus lambda I. Si is given here. So some delta will be given or added with the xi to get the next point. But the question is, how far we will move so that the function is improved, so that the function is improved. And if we repeat the process, ultimately we have to find out a band, an interval that minima will lie between these two intervals, these 2 points. We cannot find out the exact minima. We may not be possible to find out the exact minima, but it is possible by the algorithm that minima is lying between xn and xn plus 1, where the gap or width of this interval be delta. Now, if we can make delta less than equal to epsilon, epsilon is a very small value, pre-assigned small value. Suppose our accuracy required is 0.01 and we take epsilon as 0.001, and if we can make the delta less than 0.001, we can ensure that accuracy in the result, though it is not given by a fixed single point, it is given in a band, it is given in an interval, still we can claim the accuracy is as per our desired level. So in numerical method, generally we will not arrive at the exact minima of or maxima of the function. Instead of that, we can identify an interval within which the minima is surely existing and the width of the interval is less than certain epsilon, which can ensure our accuracy. Is it understood or not?
Yes, sir.
Any question? Any question?
No, sir. Not from my side.
So suppose by numerical method we are not getting exact solution. Still, why it is acceptable? What will be the answer?
So
Rohan?
we can minimize the error to our desirable level.
Yes. So even it is an interval, but length of the width of the interval is matching with our accuracy demanded, so we can be satisfied with that. Is the question answerable to everybody? Hello?
Yes, sir.
So there are so many algorithms in optimization. Now I am giving the demonstration of some traditional algorithm. First of all, we can classify traditional and non-traditional. In traditional algorithm, we will use the concept of algebra and calculus to find out the minima. And there are certain other algorithms where some natural phenomena will be followed to identify the minima, which are under non-traditional algorithm. Under traditional algorithm, also there are certain class, suppose bracketing method. In bracketing method, the objective or philosophy is always at every iteration, you have to identify a narrower interval within which the minima must lie. And if you repeat the process and make this interval narrower and narrower, ultimately you will arrive at your desired accuracy. But always your logic will be that minima is lying within this interval, and interval is less or rather narrower than the previous one. This is the logic of bracketing method. In case of region elimination method, the reverse thing. You have to place certain logic where minima must not lie, and that portion will be subtracted from your search interval. So your search interval will be reduced. And now in this way, at every iteration, you will reduce continuously. Continuously, you will reduce the search interval, and at certain iteration level, the length or width of your search interval will be compatible to your accuracy demanded. Then there you can stop. That is the convergence. Is it clear or not?
Yes, sir.
Yes, sir.
And in interpolation method, some functional form we will assume, and for that particular functional form we use some classical technique, and then we will approximate the curve. I will discuss later. So bracketing, region elimination, and interpolation. Under bracketing method or even under region elimination method, another classification is there: direct search and gradient based. I will discuss certain algorithm where only we require to evaluate the function value of the objective function. And then using certain logic, we can arrive at our minima or maxima. We need not to calculate the derivative, neither first order derivative nor second order derivative. Those are called direct search method. There are other methods under the bracketing, under the region elimination, where along with the function value, we need to calculate the gradient of the function because algorithm demands it. Where we have to use the gradient value also, first order derivative, second order derivative, then the methods are called gradient based methods. Under direct search, there may be the function may be single variable, function may be multivariable. And also in the problem, there may be constant, there may be no constant. If constant, then it is constant optimization problem. If there is no constant, it is unconstant optimization problem. Now, before going to discuss the algorithm, first of all, we are starting with some assumption that the objective function is unimodal. Do you understand what is meant by unimodal and multimodal? Hello?
Some function that has only one minima or one maxima.
In the given interval. Yes.
Yes, sir.
So the left side picture is unimodal and right side it is multimodal. Why we are assuming unimodal? Because while we will discuss the capability or ability of the search algorithm, we will look that using the logic of searching minima and maxima, some algorithm can pick up a local minima. Suppose in this right side, this is a minima and this is a minima. Both are minima, but this is the global minima and this is not the global minima. But our logic algorithm may be capable to identify these as minima from the given problem, but algorithm may be trapped finding this point as minima. It cannot distinguish between the local minima and global minima because the logic using by this algorithm is such that it cannot distinguish between the local minima and global minima. Then it can arrest or it can be trapped at a local minima. So the capability of algorithm, whether it can search a global minima or not, that will be the capability. In the beginning, we will rather discuss certain algorithms which are not capable to distinguish between global and local. So therefore, a function is required which contains only one minima where there will be no question of local minima, global minima. That function is called unimodal function that is shown here. So now the algorithm we are going to discuss are suitable for unimodal function. In case of multimodal, they can be trapped or they can give you a local minima as minima of your objective function, which is not true. Is it clear?
Yes, sir.
So already I have discussed this slide. Let us start with certain algorithm. How the actual algorithm works. Suppose the first algorithm is bracketing method. Under bracketing method, it is direct search method because here we will not calculate the derivative of the function. Only function values will be compared to identify a minima. Okay. The name is exhaustive search method. Clear? Suppose the search interval is given by xs and xf. Xs is the starting point, xf is the final point. This is the search interval where there is a single minima and we have to identify that value. This is our target. Okay. Hello?
Yes, sir.
Okay. So now first find out the value of delta depending on your accuracy demanded. Get the value that xf minus xs divided by n is equal to delta. Okay. Delta will be obtained by xf minus xs divided by n. The search interval divided by n is the value of delta. And now we are starting with x1, x2, x3. x1 is equal to xs, x2 is equal to x1 plus delta, and x3 is equal to x2 plus delta. We have 3 points, successive points, x1, x2, x3. At the first iteration, x1 is equal to xs and x2, x3 are the next successive 3 points. Clear?
Yes, sir.
Now you evaluate the function value at these 3 points, fx1, fx2 and fx3. Now you check a condition whether fx2 is less than fx1 and fx2 is less than fx3. You have a fx2, fx1, fx3. You just check whether your fx2 is less than fx1 and fx2 is less than fx3. If this condition is satisfied, then we can say that the actual minima must lie between x1 and x3. Is it acceptable to you or not? Hello?
Sir, can you repeat that
Yeah.
portion once?
Suppose we are checking 3 successive points, fx1, fx2, fx3, the function value. And now if this condition simultaneously satisfied, that fx2 is less than fx1 and fx2 is less than fx3, that means the value of the function at the middle point is less than the left side and less than the right side. In that case, we can say that minima of this function must lie between the left point and the right point, x1 to x3.
Yes, sir. Yes, sir.
It is without exception, it is always true. Do you accept or not?
Yes, sir.
So if this condition is achieved, then we can mark optima must lie between x1 and x3. You just recall in the algorithm, I already told that in numerical method we will identify 2 boundary line within which minima is there. So here x1 and x3 is the boundary. Now you can say ultimately we have to place only one solution. What solution do we place? You can write x1 as minima, you can write x3 as minima, you can write x1 plus x3 by 2 as minima. Any point you choose within this interval, your accuracy will not be disturbed. If you can reduce the x3 minus x1 up to your accuracy level. Is my point clear or not?
Yes, sir.
And selection of n will be such that here what is the interval within which minima lie? It is 2 delta. So 2 delta will be compared with my accuracy level and we can choose appropriate n to make 2 delta less than epsilon.
Yes, sir.
And after getting x1, x3 as the boundary, what will be the maximum error possible? Maximum error possible is 2 delta. Suppose the actual optima is just adjacent to x3, but we are choosing x1 as minima. Then what will be the loss in accuracy? Less than 2 delta.
Yes, sir.
So whatever the point I choose between x1 to x3, the maximum error will be of value 2 delta. Do you accept?
Yes, sir.
And 2 delta can be made less than epsilon but by choosing appropriate n. Do you accept?
Yes, sir.
So even we can find some boundary or interval as optima, it will not hamper our accuracy. It is accepted or not.
Yes, sir.
But at the first iteration, this condition may not be satisfied. Then what to do? If it is satisfied, then we identify the interval. But if not, then we have to check whether already we have crossed the final length and the x3 is less than xf or not. Because at certain iteration level, we will continue the process, and at certain iteration, x3 will be xf. These last 3 points.
Yes, sir.
If it is not the last 3 points, then you just make shift one interval. You make x1 is equal to x2 and go back to the step 2. Clear?
Yes, sir.
So what now happened? Now x1, x2, x3 is shifted by one interval at the right side. Now this actually x2, x3, x4 will be compared.
Yes, sir.
You can get the minima here or not. Then again it will be x3, x4, x5, x4. In this way, it will continue up to x7, x8, xf.
Yes, sir.
Either within this interval, it can once satisfy this logic and obtain the interval or not. It may happen that the total intervals are compared, but never this logic is satisfied. It may happen. It depends on the position of the points, actual minima, and the search interval length delta. Is it clear or not?
Yes, sir.
If this happens, then we have not got our minima. So what to do? Then we have to make n is equal to 2n. We will subdivide with more fine interval. Clear?
Yes, sir.
And repeat the process. We will make n is equal to 2n and we will go step 1 where the delta will be modified, and will again the same process will be continued, and hope we will get. If we do not get, we again to make it finer and finer until we get a solution. This is called exhaustive. Is it understood or not?
Yes, sir.
Now we will discuss that this exhaustive process is very slow and it will take much time, but we can make the process accelerating our search process using certain logic, which is called accelerated method or sometimes called bounding phase method. In this method, first of all, we will start with an arbitrary initial solution, okay, in the search interval AB. We will start with an initial solution arbitrarily chosen, x1 suppose. Clear?
Yes, sir.
And some initial step size delta. So first we will choose x1 and delta. Now we will assume two value x2, one is equal to x1 plus delta and x3 is equal to x2 plus delta. So we have three values, x1, x2, x3. x2 is right side of x1, x3 is right side of x2. Now we can evaluate fx1, fx2 and fx3. Clear?
Yes, sir.
Now if we check this logic that fx3, the rightmost point is less than the middle and the middle is the less than the left, x1. If this condition happens, fx3 is less than fx2, fx2 is less than fx1, then can we say that the minima must lie at the right side of the x1? You follow my point?
Yes, sir. Yes,
We
yes, sir.
cannot say where the actual minima is. We cannot identify interval of the minima, but we can say, if this logic happen to be true, that minima lies at the right side of the x1. x1 is arbitrarily chosen. I have no idea. x1 is arbitrarily chosen. So minima can be at the right side of x1, minima can be at left side of x1. By this checking criteria, we can confirm whether the minima is at the right side of x1 or left side. If this is not true, but if this is true, supposed to be, then we can say minima must lie at the left side of the minima. Do we agree or not? Hello?
Yes, sir.
So first, by checking these two criteria, you have to confirm the direction of search. Because if minima lies at the right side of x1, then onwards we will search from x1 to right side. But if it is left side, we will start from x1 to left side. So first, search direction is identified by evaluating three function value and applying this logic. Do you agree or not?
Yes, sir.
Now say, if both the logics are not true, then what will happen? It may happen that neither of the logics are true.
So then the minimum might be in between.
Yes, very good. So then it is it will be eventual rather that minima is obtained between x1 and x3. So suppose that is not available, but we have identified the value of delta, whether delta will be positive. If we have to search in the right direction, delta should be taken as positive. And if you have to search in the left direction, delta should be taken as negative delta. Do you agree or not? What is the meaning of this making delta is equal to delta and delta is equal to minus delta?
Yes, sir.
So now we are confirmed. We have x1 and we know the search direction by choosing or giving proper sign to delta. Now suppose we are starting another algorithm within this algorithm, which is called the accelerated step size algorithm. Now suppose k is equal to 1 and we are writing x2 is equal to x1 plus 2 to the power k into delta. x2 is equal to not x1 plus delta, but x2 is equal to x1 plus 2 to the power k into delta. At this iteration, actually the shift of the point will be 2 delta as k is equal to 1. Okay. Hello?
Yes, sir.
And now evaluate fx2. We are confirmed that minima is in this search direction. Now, if fx1 is less than fx2, x2 is in the search direction of the minima. Depending on the position of minima, it can be at the left side or at the right side. But in the search direction, if the value is more than the x1, then we can say that fx1 is less than fx2 means the value is more than the fx1. Then we can say that it has exceeded the optima, isn't?
Yes, sir.
So then optima lies between x1 to x2.
Yes, sir.
What is the interval? 2 delta, isn't? Difference between x2 and x1 is 2 delta.
Yes, sir. Yes, sir.
At this k is equal to 1.
Yes, sir.
But if not true here, then it will again come to top level. Now make k is equal to 2. Just making k is equal to k plus 1. Now k is equal to 2. Now if it choose again select x2, x2 will be now x1 plus 2 to the power 2 into delta. That means 4 delta. Is it clear?
Yes, sir.
Now it will again check whether fx1 is less than fx2 to confirm whether it exceeded the crossed the minima or not. If it happens, then again it will write minima lies between x1 and x2. But interval is here 4 delta, isn't?
Yes, sir.
Even if here not happen, in the next step happens, then interval will be 8 delta.
Yes,
Do you
sir.
agree? But
Yes, sir.
it will converge very fast, as because the interval is very large, it will converge very fast and will ultimately give you the interval within which your minima is lying. And what will be the accuracy obtained? It depends at what iteration level it have got. The maximum error possible is given by 2 to the power k into delta.
Yes, sir.
So rapid convergence but larger uncertainty, lesser accuracy with this method. Do you agree?
Yes, sir.
Then somebody can ask, if accuracy is not achieved, why should we use this algorithm? The answer is like that. When we are tuning some performance, we use two type of controller. One coarse controller, another finer controller. Suppose somebody, if you try to catch the radio signal, first you move with very fast, then you make it slow, isn't?
Yes, sir. So with this method, we are just trying to catch the region where the optima might lie, and then we will use fine tuning.
Yeah. Because suppose your search interval is of width 1000. If you use some finer method within this larger interval, it will take much time. But rather, you first use this accelerated method, make the interval 10 instead of 1000. 10 is not your matching with your accuracy demanded, but 1000 can be made to 10 within a very short step. Then use some finer algorithm to make 10 to 0.01, and the total time taken by both the algorithm will be minimum compared to using a single finer algorithm. Is the point clear?
Yes, sir.
So utility of this algorithm is there, though the uncertainty margin or accuracy level is poor compared to other, but convergence rate is very fast. So the previous two algorithms that I have discussed are under the bracketing method. Now we are discussing region elimination method. What is the basic logic or basic philosophy? First of all, you have your search interval A and B. Clear?
Yes, sir.
AB is known. Now you choose two intermediate points within AB such that x2 is greater than x1. Evaluate fx1 and fx2. And now again check the logic. Suppose it is a unimodal function, x2 is at the right side of x1 and fx1 is greater than fx2. Fx1 is greater than fx2. That means it is still reducing. It is still reducing
Yes, sir.
in the right direction. While moving in the right direction, it is still reducing. What does it indicate? X1 is at the left of the minima or not?
Yes, sir.
Then we can eliminate region between A to X1. Do you agree or not?
Yes, sir.
This is the logic, that we can identify a region which can be eliminated. Similarly, if suppose instead of fx1 greater than fx2, we find fx1 less than fx2. x1 is at the left side of x2 and towards moving x2 to x1 it is reducing. So we can at least say that position of x2 is at the right side of the optima.
Yes, sir.
So then b2 x2 can be eliminated.
Yes, sir.
Do you agree with the logic?
Yes, sir.
And eventually or incidentally, if it is observed that neither of the two logic is satisfied, rather fx1 is equal to fx2, then we can again say that minima lies between x1 and x2.
Yes, sir.
Then a2 x1, b2 x2 both are eliminated.
Yes, sir.
And while eliminated, suppose when the a2 x1 region is eliminated, our search interval converted from AB to X1B, isn't it? Is reduced.
Yes,
So
sir.
at every iteration, you can reduce the search interval, and gradually, through several steps, a point will come when your converted search interval is comparable with your accuracy level. Then you stop. Take any point within the interval as your optimum point. You can achieve your accuracy.
Yes, sir.
So this is the logic of the region elimination method. Now some specific region elimination method where this logic has been applied. One of such method is called interval hubbing method. Okay. Here, instead of 2, 3 intermediate points have been chosen with equal interval size. The total interval is now parted into 4 equal interval: A, x1, xm, x2, b. Is it clear? Xm is the midpoint between A and B. X1 and x2 quarter apart from the boundary.
Yes, sir.
Now, taking A, x1 and xm, you can eliminate either x2 to xm or a to x1, because earlier we have discussed that if we take 2 intermediate points, then one of the region can be eliminated while we will compare. So suppose first we are checking this interval. A and x2 is the interval, x1 and xm are the intermediate point. So checking whether fx1 is greater than fxm, either a to x1 or xm to x2 can be eliminated.
Yes, sir.
Or now again we can compare this logic with xm, x2 and b.
Yes, sir.
Another portion can be eliminated. So at every iteration level, evaluating 3 function value, we can eliminate 50%, because one interval is quarter, no, 25% of the region.
Yes, sir.
So in 2 logic, if we can eliminate 2 region, 50% will be reduced. Search will be reduced by 50% at every iteration level.
Yes, sir.
So the name is interval hubbing method. At every iteration, interval is being hubbed. Is it clear or not?
Clear, sir.
So after such n iteration, the width of the search space will be reduced to b minus a divided by 2 to the power n.
Yes, sir.
So you can get the idea of n by comparing the interval and your accuracy demanded, that what number of steps will be required.
Yes, sir.
Now, one thing I have to share with you, that so far we have discussed about how it is possible to identify a region where existence of minima can be established. While doing this, we have to use computer program. And during the execution of the program, 2 types of actions. One is evaluating arithmetic function and another is logical statement, isn't?
Yes, sir.
So when functions are being evaluated, that is under the arithmetic operations. And when logical comparison is there, then it is the logical function. But time taken by the arithmetic functions are more compared to logical by the computer. So ultimately, time taken by the algorithm to converge will depend how many function values are evaluated. How many function values are evaluated in every iteration. Is my point acceptable or not?
Yes, sir.
So, to reduce the burden of the computation time, it will be our effort to reduce the number of functions to be evaluated as much as possible. If possible, it will make the algorithm effective. Is it acceptable or not?
Yes, sir.
So now people started to think in this way. Logic is same, that we have an interval, we will take two intermediate points, evaluate the function of those 2 points, compare them, identify the region to be eliminated, reduce the interval, next again do it. This is the logic.
Yes, sir.
And in this logic, in the first iteration, the two intermediate points, and when we are going to the next iteration, one of the intermediate point still remains as intermediate point. Do you agree or not?
Yes, sir.
Because if a2 x2 is eliminated, then x1 remains valid as intermediate point in the next iteration. And if b2 x1 is eliminated, then x2 remains valid as intermediate point.
Yes, sir.
But if your scheme of selection of intermediate point is not properly chosen, then you cannot accept the x2 as intermediate point by the same scheme. Suppose in the previous one, here we have chosen that x1 is equal to a plus 0.25 of the b minus a interval, isn't it?
Yes, sir.
And xm is the midpoint and x2 is b minus quarter. But when suppose these lengths are eliminated, region is eliminated, suppose a2 x1 is eliminated, then x1 does not remain the midpoint of the residual interval.
Yes, sir.
x2 is not the quarter from b.
Yes, sir.
So every point, if we use the same scheme of selection of intermediate points, so new points will arise. And we have to evaluate function at the new points again.
Yes, sir.
But can we think of selection of intermediate point in such a way that if one of the region is eliminated, after eliminating the region in the residual region, the point which is still as intermediate can be a candidate using the same scheme? Because within the algorithm we cannot change the scheme regularly. Is my point clear or not?
Sir, can you repeat once?
My point is that how we are selecting the intermediate point, that is given by a particular formula.
Yes, sir.
At every iteration, the same formula will be used.
Yes, sir.
But if interval, boundary of the interval changes using the same formula, we cannot get the intermediate point which is remaining from the previous iteration. It may not be possible.
Yes, sir.
But now we have to think, can the formula be chosen in such a way that even after the elimination of the region, if we apply the same formula in the residual interval, one of the previous intermediate points can be intermediate point in the current iteration? Is it possible or not? People try to think in this way. You may say, even if it is possible, what is the advantage? We need not to evaluate the function value of that point. It is already there. Is it acceptable? that it is advantage?
Yes, sir. Yes, sir. It is an advantage. We can avoid the calculation overhead.
So number of functions to be evaluated can be reduced. So suppose we are taking a scheme that we are choosing a value tau. Tau is a value between 0 to 1, a fractional part. And first of all, when k is equal to 1, we are selecting that a1 is equal to a, b1 is equal to b. This 1 stands for iteration level. At k is equal to 1, a1 is equal to a, b1 is equal to b, and the interval L1 is equal to b1 minus a1 means b minus a. Okay. We identify the left side boundary, right side boundary, and length of the interval L. At iteration level k, all of them are having suffix 1. Accepted?
Yes, sir.
Now we are choosing the selection of intermediate points x1 is equal to a1 plus tau into L1. Tau is a value less than 1. a1 plus tau into L1. Okay.
Yes, sir.
And x2 is equal to b1 minus tau into L1. x1 is tau L1 apart from A, and x2 is tau L1 apart from B in this direction. So these are the 2 points, x1 and x2. Clear?
Yes, sir.
And suppose now we evaluate x1, fx1 and fx2. Okay? Depending on the value of fx1 and fx2, one of the region, either a2x2 or b2x1, will be eliminated.
Yes, sir.
While eliminated, what is the remaining part? Look, remaining part is tau L.
Yes, sir.
Either this portion is eliminated or this portion is eliminated. The remaining part always will be tau into L. Do you agree or not? So
Yes,
length of
sir.
the interval in the second iteration level is tau L. Boundary is modified.
Yes, sir.
Now at k level 2, a2 is equal to x2, b2 is equal to b, L2 is equal to tau L. Do you accept or not?
Yes, sir.
a2 is equal to x2, b2 is equal to b, and L2 is equal to tau L. Okay.
Yes, sir.
Now we are applying the same formula for selecting intermediate point. Okay. x1 is equal to a2 plus tau L2. x1 is equal to a2 plus tau L2. And x2 is equal to b minus tau L2. Okay.
Yes, sir.
So look, b2 minus tau L2 is equal to b2 is equal to b. Hello.
Yes, sir.
And tau L2 is equal to tau L.
Yes, sir.
So it is b minus tau into tau L.
Yes, sir.
Suppose this x2, my intention, my desire is that it should coincide with the x1 of the previous iteration. Is it my intention or not?
Yes, sir. Yes, sir.
Because then we need not to evaluate the function value at this point.
Yes, sir.
So now the x1 is equal to a plus tau L. Look, the previous point.
Yes, sir.
We make them equate. B minus tau into tau L is equal to a plus tau L. Okay.
Yes, sir.
And rearranging the terms, we are getting an equation that tau square plus tau minus 1 is equal to 0.
Yes, sir.
And we are getting a real value of tau as 0.618 by solving this quadratic. Positive real value is 0.618. Is it understood?
Yes, sir.
So while selecting the point, we are going back to here. If we take the tau value as 0.618 and select the point, intermediate point with this formula that x1 is equal to a plus tau L and x2 is equal to b minus tau L. And at every iteration, we will modify a, b, and L and repeat the process. Then at every iteration, only one function is to be evaluated,
Yes, sir.
which enhances the strength of the algorithm because it reduces the time computation time.
Yes, sir.
This method is named as golden section method. Very important method, very popular method for single variable search algorithm. Golden section search method is very popular and very useful and effective. Is the process understood or not?
Yes, sir. Yes, sir. Understood, sir.
Now hello, audible I am.
Yes, sir. You are audible.
So I am now going to discuss some gradient based methods. The methods already discussed, interval halving and golden section, both are direct search method under region elimination. Now another region elimination method, but gradient based method. Okay. The name of the method is bisection method. Okay. Hello.
Yes, sir.
Deepnarayan,
Yes, sir.
do you have any question so far already?
No, sir. No, sir.
Konko,
Yes, sir.
do you have any question?
No, sir.
Shubhro,
No, sir.
Partho,
No, sir.
Rohan,
No, sir.
Ananya,
No, sir.
Arijit. So, okay, now we are going to discuss bisection method. Suppose the interval is given by A and B and there is a single minima within A and B. It is already known. Okay. Now select a midpoint xm as a plus b by 2. Calculate the derivative at these points f1a, f1b and f1xm. You have to calculate derivative using numerical methods. I have already shown, because for calculating derivative by numerical methods, you have to evaluate only the function values at the points. Do you agree or not?
Yes, sir.
Function is given, points are known, a, b and xm. We can evaluate f1a, f1b, f1xm. These are the derivatives. Now you will check whether f1a into f1b is less than 0 or not. হবে তো?
Sir, F1A and F1B's multiplication value is less than 0. That means they are of opposite signs.
That means x optima must lie between them.
Yes, sir.
It is a checking criteria just.
Yes, sir.
Then you check f1a into f1xm is less than 0 or not.
Yes, sir.
If it happens to be true, what conclusion we can take? That minima must lie between a and xm.
Yes, sir.
So b to xm will be eliminated.
Yes, sir.
We have to make b is equal to xm, a is equal to a, and go to next step, isn't?
Yes, sir.
If it doesn't happen, if the reverse f1a into f1xm is greater than 0, so then already we have checked that f1a into f1b is less than 0. So f1a and f1b are always opposite side. It is already proved.
Yes, sir.
Now if f1a into f1xm greater than 0, then we can eliminate a to xm, making a is equal to xm for the next iteration.
Yes, sir.
So just calculating the derivative at 3 points and then checking this logic, we can eliminate 50% of the region at one iteration. Therefore, it is known bisection. Is it clear or not?
Yes, sir. Clear, sir.
And now if we repeat this process, naturally within n iteration, it will, the total interval will be reduced to b minus a divided by 2 to the power n, and every time it is divided by 2.
Yes, sir.
So we can achieve our accuracy in a very faster method. This is called bisection. Very easy, convenient method. Only you have to calculate derivative at 3 points. And look, for calculating one derivative, you need to evaluate two function values.
Yes, sir.
So that is the concern, because it will increase the time requirement. Okay.
Yes, sir.
This is the bisection method. And this is the extension of the bisection method. It's called secant method. Secant method uses the, because in case of bisection method, we uses the only sign related information of the derivative, not the value of the derivative, isn't it?
Yes, sir.
But the relative value of the derivative also indicates some hints about the position of minima, which has not been used in bisection method, that is used in secant method. Okay.
Yes, sir.
What is the assumption, or what is the formulation? Suppose like AB, you are calculating the derivative f1a, f1b at points A and B. Okay. Checking that f1a, f1b product less than 0, ensuring the existence of minima within A and B. Now you, instead of selecting xm as the midpoint of the two, rather you can guess the position of the optima using this method. Here the assumption is that the gradient varies linearly. Suppose fx is a curve. Okay. Hello.
Yes, sir.
At every point we can evaluate the gradient of this curve.
Yes, sir.
And if we assume that the variation of the gradient is linear, we know f1a here, we know f1b, we can join the line, we can get the line, and if we say that the gradient of these functions varies linearly, then this is the line along with which will vary.
Yes, sir.
And if it is, if our assumption is true, then where the minima will lie, where the gradient is 0.
Yes, sir.
So at the point xm, what is the position of xm? Xm is such a point so that the gradient on the curve will be 0.
Yes, sir.
So now a straight line having two endpoints known. This is A f1a, this is B f1b. Do you agree or not?
Yes, sir.
Yes,
And
sir.
intermediate point xm where derivative, where fxm is 0. Do you accept or not?
Yes, sir.
So I think xm can be evaluated by interpolation method,
Yes, sir. Yes, sir.
because this minus this by this minus this, you know the gradient interpolation formula. So from there, the position of the minima can be guessed with this formula. Okay or not?
Yes, sir.
It is nothing but that f1b minus f1xm, okay, divided by b minus xm is equal to f1b minus f1a divided by b minus a. So from here xm can be evaluated.
Yes, sir.
A known, B known, f1a known, f1b known, fxm is known because it is here 0. Only unknown is xm. Now what is the advantage? Instead of, in case of bisection, it was possible to eliminate 50% of the region, taking xm as the midpoint for checking. But now here we have checked xm, which is very close to the actual optima. Okay. So more region will be possible to be eliminated in one iteration.
Yes, sir.
This is called second method. Once you are getting xm, then the process is same like bisection method. You have to compare and you have to eliminate. Is it clear or not?
Yes, sir.
Yes, sir.
So once we get the xm,
Yeah.
that will be like a will be equal to a and b, like one of the point will be like in its place and other point will be replaced by xm. So
While
then,
getting xm, then you evaluate fxm because actual derivative is not zero.
yes, sir.
It
Yes,
may
sir.
be positive, it may be negative, it may be because this calculated point may be at the right side of the actual optima, maybe left side at the actual optima.
Yes, sir.
Depending
Yes,
on
sir.
that, fxm will come.
Yes,
Okay,
sir.
and then you check like the bisection whether this is less than 0 or f1b into fxm is less than 0 to identify what region is to be eliminated.
Yes, sir. So my question is like, there are three possibilities about the gradient of xm. That is, it can be multiplied with gradient of a and it is less than 0. In that case, the optima lies between a and xm.
Yes.
So in that case, can we again apply the second method for guessing another xm?
Yeah, we have to continue this process. At one iteration, it will not be finalized.
Yes, yes, sir.
Until the interval is as per our desired accuracy, we have to continue it.
Yes, sir. That is my question. Thank you, sir.
The difference is that in the bisection method, the intermediate point is straightforward midpoint.
Yes, sir.
We have not used the information of the magnitude of the gradient to gauge the where actual minima can lie. Here, some attempt has been made. Assuming the derivative varies linear, we have gauged the position of xm and then applied the bisection rule. Logic is same.
Yes, sir.
Is it understood or not?
Yes, sir. Clear, sir.
So today up to this, I think these are my presentation on single variable unconstant optimization algorithm, but there are certain other algorithms. I will give you the list. If you are interested, you can go for that also. And if you have faced any problem, you can discuss with me. Do you have any are you getting any idea that how this algorithm will work to find out the minima or maxima of a unimodal single variable unconstant optimization problem?
Yes, sir.
And if I give some example, and I think you can execute at least two steps. ধরো ফাংশনটা দেয়া রইল, ইন্টারভ্যাল দেয়া রইল, বলা হলো গোল্ডেন সেকশনে দুটো স্টেপ করে দেখাও।
Yes, sir. Yes, sir.
তো দুরকম ভাবেই কোয়েশ্চেন থাকতে পারে। অ্যালগরিদমটা লেখো বলতে পারি, এক্সপ্লেন দ্য প্রসিডিওর বলতে পারি, অথবা একটা ফাংশন দিয়ে তার দুটো স্টেপ করে দেখাও এটা বলতে পারি।
Yes, sir.
কোনোটাতেই অসুবিধা হবে না।
না স্যার, হওয়া তো উচিত না।
আচ্ছা, এখন অবধি কজন আছো? অনন্যা,
হ্যাঁ স্যার।
অনির্বাণ, অনির্বাণ দে, অরিজিৎ সাহা, দীপনারায়ণ,
Yes, sir.
দীপায়ন,
জি স্যার, অরিজিৎ আছে।
Yes, sir.
পঙ্ক,
Yes, sir.
পার্থ,
Yes, sir.
ঋষি,
Yes, sir.
রোহান, রোহান,
Yes, sir. Yes, sir.
শুভ্র,
Yes, sir.
তো 81 জন এই ক্লাসের স্টুডেন্ট।
স্যার অরিজিৎ আছি স্যার, ও মাইকটাও গন্ডগোল করছে।
হ্যাঁ, তোমারটা পেয়েছি। অনির্বাণ তো নেই, ও তো ছবি রেখে চলে গেছে। 81 জনের মধ্যে এই 10 জন আছো, মানে বাকিদের কি ক্লাস করবার দরকার নেই? তোমরা 10 জন কি অফলাইন করতে পারো না? তোমাদের অসুবিধা আছে? অনলাইন পড়ালে হচ্ছে, তোমাদের অসুবিধা হচ্ছে না? তোমাদের পক্ষে কোনটা কমফোর্টেবল, অফলাইনে পড়া না ওই অনলাইনে পড়া?
So online better, I guess.
আচ্ছা, ঠিক আছে, তাহলে এটাই চলবে। কিন্তু মুশকিল হচ্ছে যে বাকিরা তো ক্লাসে নেই। কম্পিউটার সায়েন্সের কে আছে?
স্যার আমি আছি।
তোমার বাকি বন্ধুরা কোথায়?
স্যার অ্যাকচুয়ালি আমি মেনশন করেছি, কিন্তু বুঝতে পারছি না আসছে না কেন।
সিভিলের কে আছো?
স্যার আমি।
পার্থ,
হ্যাঁ স্যার।
তুমি কি জানো বাকিরা আসছে না কেন? কোনো খবর আছে?
স্যার সিভিলের স্টুডেন্টই কম।
4 জন আছে, 4 জনের মধ্যে তুমি একা।
না স্যার
না স্যার, আমরা আছি ওই শুভ্র।
না স্যার, না স্যার আমিও আছি।
ও, তোমরা সিভিলে, তাহলে সিভিলের অ্যাটেন্ডেন্স তুলনায় বেটার। ইলেকট্রনিক্স এর কে আছে?
Sir, আমি
দীপনারায়ণ, তোমার বন্ধুরা আসছে না কেন, কোনো খবর
স্যার
আছে?
অ্যাকচুয়ালি গেটের জন্য।
আচ্ছা আচ্ছা, তাহলে আমি পরের সপ্তাহে বেটার এক্সপেক্ট করছি, তাই তো?
ইয়েস স্যার, আই গেস 11 পর্যন্ত মোটামুটি এক্সাম আছে, দেন দে ক্যান কাম।
ঠিক, এক্সপেক্ট। ওকে, তো নেক্সট সোমবার 4:30।
ইয়েস,
ওকে, থ্যাংক ইউ।
থ্যাংক ইউ স্যার।